Welcome to the session on market design applications. We're hybrid, so we're starting in the virtual world with Patrick Hummel presenting on efficient capacity provisioning for firms with multiple locations, the case of the public cloud.
Thank you, Scott. And hopefully when I start full screen mode, people can see the full slide. And yeah, I'm going to talk about efficient capacity provisioning for firms with multiple locations, the case of the public cloud. This is joint work with Michael Schwarz, who's a colleague of mine at Microsoft. And so there are a wide range of settings in which there's a firm that has multiple locations, such as grocery store chains with multiple grocery stores, restaurant chains with multiple restaurants. And in each of these settings, the chain must decide how much inventory to provide in each location, what prices to charge in each location, and how to advertise the different locations to try to steer customer demand towards one location or another. And then another such industry that's especially relevant to the tech sector is the public cloud. And so public clouds provide computing capacity, which can be rented on demand for computation. And in the US, the three largest public clouds are Amazon Web Services, Microsoft Azure, and Google Cloud. And each of these public clouds has dozens of different regions around the world. Now, not all regions are created equal. The regions will differ in their size, what prices they charge, and their utilization rates, so the fraction of computing capacity that's being utilized by a customer at a given point in time. And the regions will also differ in their costs, and differences in utilization rates between different regions will be a key driver of cost differences between different regions, because that reflects how much capacity the cloud provider had to provide to meet a given amount of demand. And again, in this setting, the cloud provider has to answer the questions of how the cloud provider wants to provision capacity and set prices in different locations, and how the cloud provider should try to steer customer demand towards different locations. And so we sought to answer these questions in this work. And the work that we're doing here, it's motivated by a real business problem that we encountered at Microsoft. And so the particular practical problem that's motivating this work is the question of whether internal Microsoft Cloud customers should be encouraged via internal pricing or some other means to use the regions with the lowest capacity utilization rates. And at first glance, this might seem economically optimal. I mean, after all, by encouraging those customers to use the least utilized regions will improve utilization rates in those regions and help those regions achieve better economies of scale. But by analyzing the problem more deeply, we discovered that actually the opposite strategy is economically optimal, and steering customers towards regions with high utilization rates, which tend to be larger regions which have already achieved better economies of scale, can lead to a noticeable cost savings. And in this work, we'll illustrate both why this is true theoretically and then also empirically using data from Microsoft Azure. OK, so now I want to get into the notation, the model that we use in this work. So we let N denote the number of potential customers in a region. We let D sub I denote customer I's demand. D, the sum of the DIs, is total demand. C denotes the cost of a unit of compute. V denotes a customer's value for a unit of compute. Q denotes the amount of compute supplied, and then P denotes the price that's charged for a unit of compute. And in our paper, we also make some assumptions on demand. One assumption that's a special case of the assumptions that we make in our paper is the assumption that each customer's demand is an independent draw from some distribution with bounded support. In our paper, we actually impose a less restrictive assumption that allows for the possibility that different customers' demands are correlated. And then the key assumption that we make on customer demand is outlined in this slide. We just assume that for large numbers of customers, that the distribution of total demand will converge to some distribution with mean mu of n and standard deviation sigma of n, where mu and sigma are increasing functions of n. The ratio of sigma to mu, so the ratio of the standard deviation to the mean, is decreasing in n, and then sigma is a strictly concave function of n. And in this setting, the cloud provider will choose capacity Q to maximize expected efficiency, knowing the distribution from which customers' demand is drawn, but not knowing the actual realization of customer demand. And then uncertainty about the actual demand will be revealed after capacity is chosen. And then finally, the cloud provider will set some price P that's increasing in average cost. So the cloud provider will use lower prices in regions that have lower average costs. Okay, and so this is the model that we use. And I now want to get into the results that we present. So our first result is a preliminary lemma, which illustrates that the cloud provider will choose capacity in such a way that the probability there will not be enough capacity to meet demand is C over V. And the reason for this is that the marginal value of an additional unit of capacity is just equal to the product of V times the probability that the existing capacity will be insufficient to meet demands, because it's only if the existing capacity is insufficient to meet demand that an additional unit of capacity will have value, because it enables the cloud provider to meet additional demand. And so to maximize efficiency, the cloud provider just sets this marginal value equal to marginal costs, and thereby chooses capacity in such a way that the probability that there will not be enough capacity to meet demand is C over V. Okay, and so our next result concerns the relationship between unfilled demand and region size. And so here we show that the expected fraction of demand that will be unfilled will be lower in larger regions. In this slide, we spell out the mathematical reasons for why this is true, but the high-level intuition for why this is true is that in larger regions, there's less uncertainty in demand relative to expected demand. And so that means that in these rare cases where demand exceeds capacity supplied, that on average, demand will exceed capacity by a smaller percentage in a large region than it does in a small region. And so for that reason, the expected fraction of demand that will be unfilled will be lower in small regions. Our next result concerns the relationship between prices and region size. So here we find that the cloud provider will set lower prices in larger regions. This follows from our assumption that the cloud provider will use lower prices in regions with lower average costs. In this slide, we spell out why average costs are going to be lower in larger regions. And that's the high-level intuition for why that's true. That is that in large regions, there's less uncertainty in demand relative to expected demand. So the cloud provider does not need to provision as much capacity relative to expected demand in order to maintain a high probability of having enough capacity to meet demand. So average costs will be lower in larger regions, and prices will also be lower in larger regions. So our next result concerns the relationship between marginal capacity costs and region size. And so here we find that the incremental capacity cost resulting from adding another customer to a region is going to be lower in larger regions. So in this slide, we spelled out why this is true by just giving an expression for the incremental capacity costs, and the result then follows from the concavity of sigma as a function of n. But the high-level intuition for why this is true is that in larger regions, the cloud provider does not need to provision as much capacity relative to expected demand in order to have a high probability of having enough capacity to meet demand. So that also means that if we add another customer to that region, that the cloud provider will not need to provision as much additional capacity in order to maintain a high probability of having enough capacity to meet customer demand. So our next result concerns the relationship between the incremental unfilled demand and region size. So here again, we find that the incremental expected amount of unfilled demand that results from adding another customer to a region will be lower in larger regions. And in the slide, we've given a mathematical expression for this incremental unfilled demand, and the result again follows from the concavity of sigma as a function of n. And the high-level intuition for why this is true is just that in larger regions, we have a lower fraction of expected unfilled demand. And so that also means that when we add another customer to a larger region, that in expectation, that will cause less additional unfilled demand than if that customer had been added to a smaller region. And so when you combine this result with the result in our previous slide, it follows that it's better for a cloud provider who can send a customer to either a small region or a large region to send that customer to a large region, as that will cause both less additional capacity costs and also less incremental unfilled demand. Okay, and so in this work so far, we've been focused on customers who, although they might have the flexibility to deploy to either a small region or a large region, once they've been deployed to a particular region, they need to stay in that region in perpetuity, or at least until they deallocate their workloads. You might imagine that some customers could be even more flexible than this and actually have the flexibility to migrate their workloads from one region to another after they've been deployed. And in our paper, we also present an analysis of these so-called hyperflexible customers, which we model as customers who can be deployed in a region after observing the demand of other customers. I won't get into too much detail on this since this is a short talk, but at a high level, we do find these hyperflexible customers can have a significant impact on capacity provisioning. For instance, if there is a small number of hyperflexible customers, that could actually have a big impact on the cloud provider, because the incremental capacity cost of serving those customers will be very close to zero. But if there are a large number of hyperflexible customers, then at that point, the cloud provider just needs to worry about provisioning enough capacity worldwide to meet worldwide demand, and these distinctions between different sized regions would vanish. So our paper also contains some empirical results, and that largely substantiate our theoretical findings. And so our first such empirical result concerns the relationship between prices and region size. So for this, we considered 6 types of Azure VMs that are offered in each Azure region. We considered 2 different measures of region size: supply by region, which is the capacity for a given type of VM; demand by region, which is the demand for a given type of VM. It turned out that the supply and demand-based measures of region size were nearly perfectly correlated. So in these slides, I'll just present the results using supply, and then the demand-based results are nearly identical. And then in this slide, we've depicted the relationship between normalized VM price, which we define as the ratio between the price for that VM in a particular region relative to the average price for that VM in all Azure regions, versus normalized region size, which we define as the size of a region for that VM in a particular region relative to the average region size for that VM type over all Azure regions. And in the graph, you'll see a clear negative relationship between price and region size. On average, we found a correlation of -0.43 and a log correlation of -0.5. And the results for particular VM types are, each of the 6 particular VM types we considered are very close to these overall averages. And then finally, we found that the prices in the smallest third of regions are about 10 to 20% higher than those in the largest third of regions. And so we think these results are broadly consistent with our theoretical finding that the cloud provider will use lower prices in larger regions. So we also have a result on how marginal capacity costs vary with region size empirically. And so to study this, for each day in a 1-year period, we calculated total supply, total capacity supplied, and total demand in each region. We then ran a linear regression of capacity supplied on demand for each region separately. And here you can interpret the coefficients in these regressions as giving a measure of the ratio of changes in capacity supplied relative to changes in demand for each region. So they're giving a measure of how much additional capacity the cloud provider has to build out for each additional unit of demand. And so they're giving a proxy for marginal capacity costs in each region. And here we found that there was, again, negative correlation with this coefficient in region size. We found a correlation between the coefficient and region size of -0.3 and a log correlation of -0.37. And so we, again, view this result as largely consistent with our theoretical finding that marginal capacity costs will be lower in larger regions. Okay, and so to wrap things up, in this work, we found theoretically that the fraction of unfilled demand and prices will be lower in larger regions, and that the marginal capacity costs will be lower in larger regions. So if a cloud provider can go to either a large region or a small region, it's better for the cloud provider if that customer goes to a large region. And these results are consistent with empirical evidence that we find from Microsoft Azure. And that's the presentation. I'm happy to take your questions.
Woot, QED. Fantastic talk. Do we have any questions from the room? If you have questions online, please post them in the chat. Okay, hearing no questions shouted from the room, let me ask one. So this, first of all, this is fascinating, right? I really like the counterintuitiveness of, the ex ante counterintuitiveness and ex post intuitiveness. Is there any sense in which, like, somehow in a broader model where there's like more likelihood of congestion when you're near bigger customers or something? I'm trying to figure out like what would reverse the result. And the best example I've been able to come up with so far, but I can't tell, it might actually be covered in your expected utilization framework, is like if there are some really big customers in cities or whatever who sometimes need massive amounts of bandwidth.
Yeah, so it turns out that our theoretical result actually holds regardless of the size of a customer's deployment. So I might not have made that clear in the talk, but this result does not depend on whether a customer has a really large deployment or just a small deployment. In either case, the marginal capacity cost of serving that additional customer will be lower in larger regions.
Utterly fascinating. I guess it's because the whole thing just runs on expectations. Super cool. Anyhow, I love the paper. Really great.
Thank you.
Further questions? Going once? Going twice? Sold. All right, let's thank the speaker again.
Thank you.